Okay, good afternoon. Welcome to another tutorial where I say a lot. This one's going to be a haphazard walk through sort of the basic components of wall sections. This tutorial itself will live on YouTube, but I'm trying to cobble together some supplementary documentation, and that's gonna, for us, that's gonna live in the how-to folder under the X drive under tutorials. This one's gonna be the wall section, so that's there. I wanted to first start off probably focusing specifically on kind of the 400 series sheets for kind of a really cheapest chips 3-story garden style building, and kind of what these components are and what they look like and why they exist. Kind of work my way from the foundation and go up. Okay, so let's start off at the base. Now, when we do these, you've probably gone through school and learned a little bit about kind of a compacted aggregate base, and then a vapor barrier upon which you pour your concrete slab. Well, if you haven't, we're going to cover a little bit of that. There are also going to be the types of foundations that you can have. The one you kind of see here is a post-tension slab or a monolithic pour slab, and that just means that they pour all the concrete at once, and that in that concrete running horizontally, they have these steel rods that they'll pour the concrete, they'll wait about a week, and then they will come and they will tension these rods down. They're about 2 feet on center in both directions throughout the slab, and they tension the ever-living daylights out of these rods. So you're kind of in a way creating we'll call it the poor man's precast, if you will. Some people in other jurisdictions, you'll see some photos going on that it looks more like what you're used to seeing, in that they'll dig a trench and they'll pour sort of a puddle of concrete, and then they'll come back at a later date and sort of pour a second pour on top of that, and then it's just your traditional untensioned rebar in it. Okay, so let's first, when you want to talk about doing these slabs the way we do them, we almost always have a vapor barrier. All right, and that vapor barrier prevents moisture, humidity, water from moving vertically up through the slab, through the aggregate base, and creating moisture or dampness on your floor. Okay, so here's a really good example, sort of a nice 3D image of a vapor barrier installation before they pour the footing. Right, you can see the underground plumbing's already been set. They've got some sort of rebar action going on. They have their compacted aggregate base on top of the dirt. They've got, in this particular installation, they have the foundation insulation, and mercifully they're bracing the foundation insulation so that when they pour this puddle of concrete, it doesn't blow the insulation out. And here it is. Here's this little, it's usually kind of 10 mils sort of your minimum. It's usually governed by the geotechnical report and then sometimes by your radon mitigation guy. If you don't know what radon gas is, Google it. It needs to be addressed, and a lot of times the architect doesn't do radon mitigation on their own. Sometimes a plumbing engineer can do it, but most of the time radon mitigation is handled by a third-party contractor. So anyway, vapor barrier thickness, any special coatings on it, like if you have a brown field or something, for example, your vapor barrier probably needs to have sort of a resistance to chemicals, sort of a chemical resistant vapor barrier. It usually needs to be maybe 20 mils or 30 mils thick at that point. But ideally, we want to be drawing this vapor barrier. We want to say that it's supposed to be totally sealed, and we want to have it rolling underneath the foundation. Let's talk about what actually happens, right? A lot of times you can see this. They've got their vapor barrier. You can see it just sort of rolls down and just sort of puddles right there. This is a good example of a post-tension slab. You can see all these cross yellow wires. Those are those steel cables with that little yellow protective jacket on them. They will come out and they will pour this slab. They will remove all this 2x wood formwork and they will tighten that down. They're doing a good, you can see here these little, all the plumbing PVC fixtures. And a lot of them have little collars on them. That's to keep the concrete from cracking the PVC pipe as it cures. You want to protect those pipes from any sort of movement, but that's usually not in the architect's scope of work to detail out. But it's nice to, if you mention it, it's real nice to have, okay? Here is another example of it. This is the example where it's just a trench and then a puddle of concrete, and then you can see this foam. Hopefully this is okay. You can see it's kind of bagging out there, but it's not bad. The mistake, or where people get themselves sort of turned upside down or confused or sometimes bullied by contractors even, is where this below grade foundation insulation goes and then whether or not you need it in the first place, right? We covered whether or not you would need it in kind of that res check, com check video. But the real short of the simple answer for insulation, whether or not you need it or not, it basically goes like this. Anything north of kind of the Tennessee, North Carolina line, chances are good I'm going to need to add insulation to pass my res check or my com check without going totally crazy on the wall insulation and attic insulation, okay? Pretty simple, right? So here it is. This is Louisville, Kentucky, this photo. It's up north. We need foundation insulation to pass. When you do your foundation insulation, I have a lot of strong feelings about this, but this diagram from the res check really sorts it out the best, right? To meet the energy code's requirements for how foundation insulation should be installed, you should pick one of these 5 options and run with it. And I think the key takeaway here is that no matter which option you take, that pink insulation starts at the top of slab and then goes down. Now, whether or not it rolls horizontally and which way it rolls horizontally, it varies. But the key factor is that it is an unbroken, straight shot, just down until basically frost depth, right? Which for us in India, I think is 2 feet. Up north, I think it's 30 inches further north of us, but basically that's how that works. The reason it needs to start at finished floor has to do with that temperature differential, right? So you're trying to prevent a thermal bridge, right? The insulation is supposed to be a thermal barrier, okay? If you don't understand what a thermal bridge is, you know, you could find out thermal bridging like my kid did, where my wife is draining some hot boiling water and he puts his hand into that hot water from behind her where she couldn't see him. And he learned really quick how temperature from hot water transfers into his hand by a thermal bridge. You want to prevent your building from doing that, okay? The biggest delta T, the biggest temperature differential, other than air-to-air transfer, which is again dealt with by your walls, will be at the top, theoretically at the top of grade, right? We all understand that, like, as you go deeper into the ground, the temperature kind of levels out. Even though it could be minus 10 degrees outside and the top of that dirt's minus 10 degrees and it's been 10 degrees all week, I dig down 2 feet and that dirt could be 30 degrees, 40 degrees. You dig even farther, it kind of levels out at about 50 degrees for most places. So the most important place to deal with foundation insulation is usually the first 6 to 8 inches to a foot down. That's where the biggest temperature difference happens. That's where you get the most money for that insulation. So why, oh why, people think they can just put insulation horizontally and leave the slab exposed, aka the first 4 inches. It creates a huge thermal bridge. You're not getting anywhere near the value of the insulation you should get out of it, and you're not meeting building code. Period. The end. Worked around This issue comes up again and again and again. What people think they can get away with is this nonsense, where they just roll it on the backside. It doesn't work anywhere near as well as the insulation could or should work, right? Now, we have a problem in our foundations in general, okay? And that problem basically stems from the structural engineer tries to stop the insulation at a concrete slab, and you don't really want to do that. You want to have it going all the way up. Our main problem is that we need somewhere for brick to bear on, and you can't put brick on top of the insulation. It'll just squish the insulation, right? So we do have a small thermal bridge where the insulation sort of jumps back to allow the brick to have a place to sit. I don't like this detail, but you have to a certain extent, you have to reasonably adjust your details to make the building constructible. Okay, that would be my big takeaway for that. So when you're drawing these foundations, all you want to do is make sure that you're coordinating what type of foundation you've got with your structural engineer, that you're making sure you show your vapor barrier and you call it out, and you want to make sure you're showing your brick ledge, that you're calling that out. This horizontal distance is 5.5 inches. You can see this a lot of these details, right? What we do in general is on the wall sections, on the 400 series sheets, all I'm doing is kind of massing up the entirety of the wall and showing the exterior materials, but critically I'm showing the heights, right? I want to be able to, in these wall sections, to see and understand my floor to floor heights. I want to understand where I'm putting my windows. I want to understand kind of my floor assembly as a general thickness. I want to understand what my clear ceiling height will be, which in this case will be 9 feet clear, which is great. I'm going up 9 feet clear. That is a standard. I want to understand kind of how the roof works, whether or not I'm stepping back for a porch, whether or not that porch has an overbuilt gable, da-da-da-da-da-da-da. And then, because a lot of these items repeat, I want to increase the scale, right? So I'm going to jump to 1 inch equals a foot as opposed to 1/2 inch equals a foot. And then I want to provide a lot of detail, a lot of coded notes for every component in this wall assembly, right? And here I'm dealing with what everything is. So you can see pretty much all the dimensions disappear, and it's just now dealing with the naming and the installation, basically, of all these pieces, parts. So here we go. Here's the foundation. This is, got the concrete called out. I've got anchor bolts called out. I've got the width of my brick ledge called out. I could have doubled down and showed that 8-inch vertical for that brick step again. Typically in our office, we step the brick down 8 inches, provide a 1/2 inch setback, and then we fully grout behind that first course of brick. Okay. Here is where we see a lot of, I see a lot of detailing misses, especially when it comes to full bed depth stone or brick. I really want to see and understand that, you know, it basically above every opening and at the base, I want to see this flashing. Basically, you have your water channel behind your brick, or your air gap behind your brick. It's called an air gap because it's actually full of air, but it's really there for water. And it allows the water to come down your weather barrier attached to your sheathing. And then at certain critical points, you detail it in such a way that you have weep vents or weep holes in the brick. It's just a hole. It's just an opening at a brick on top of the flashing, where you have a piece of solid either fabric or metal flashing, and you allow that water to have a place to kick out of the wall. Brick is a porous material. Brick is really not a structural material unless you're using it in a very specific way. Most of the time it's just a water porous veneer, right? Water kind of scoots its way in, pushes its way in, soaks its way through. Need to have a place for it to fall down and scoot its way back out. This is also good. These vents allow the wall to dry out as well. Okay, so you'll see it. Here's my steel lintel to hold the brick. And then on top of that steel lintel, I have that flashing, and there'll be a wheat vent here that allows that water to come out. That is key. Also, masonry ties. You have to have masonry ties in brick. Brick doesn't just hold itself up magically as a single row of brick. You have to have little ties to tie it back to the wall. Okay? Different details for how you do your row lock. This is a row lock sill, just fully grouted in, have a little bit of flashing behind it. I put it underneath my windows. It's a pretty common detail. A better detail would be to use a concrete sill or a soapstone kind of precasty, stony sort of piece. The row lock isn't super awesome, but it's good and cheap, so it works, right? So there you go. Brick veneer. Make sure you have your wheat vents, make sure you have your flashing, make sure you have your masonry ties. A lot of that stuff are already noted in all your brick notes. You just have to make sure you're copying it thoroughly. Okay? Moving on, let's talk about the wall assemblies. We have our sill plate, we have our drywall, and we have our exterior sheeting. And then of course we got a little bit of trim, right? Here's the first floor. And all this is, because this wall has to be rated, is tied to an underwriter laboratory, it's a UL assembly. And all these little pieces, parts are called out. This is a 2x6 wood framed wall. Let's talk about this particular. This is our starter. You put down a 2x6 plate. You anchor it into the concrete. There are different ways to anchor it. I'm not going to get into it at this point. This particular piece, because it touches concrete, has a couple of things associated with it that you need to know. First and foremost, anytime you have wood that comes in direct contact with concrete, I won't say you have to, but for the sake of argument, you have to. Every time a piece of wood comes into contact with concrete, you need to make it treated wood. What is treated wood? Wood is treated in such a way that it's resistant to termites and water and weather in general. It's a sort of a green coating on it. You may or may not have seen it at Lowe's or your hardware store. The boards are just soaked. They're super heavy treated lumber. Don't know that much more about it, go ahead and look it up. All right. Then you get to framing. So let's talk about framing a little bit. Here is your typical framing, right? So this is a good example of, pull this over a little bit. There's your sill plate. You can see it's green. That's your treated lumber. I kind of do belt and suspenders on my first floor. I also use what's called a sill gasket. These plates often called your sill plate. And a sill gasket's kind of like belt and suspenders. It's like a little squishy water impermeable membrane that goes down on top of the concrete underneath the sill plate. And it helps keep the sill plate a little bit better protected. Okay. So from there you start framing up, you get your walls, you get your sill plate, you get your trusses, right? So let's talk about headers, right? What does a header do? Well, headers help you transfer loads horizontally at openings. You need to make room, you need to allow space, you need to allow room for a header when you're doing wood framing, right? So you can't have your window, for example, jammed up right underneath the underside of your trusses. Then there's no way for your window, there's no way to get a header to have your structural components that you need in the building, right? There's two kinds of headers. You can see how these have little stripes in them. This is your standard LVL header. It's laminated veneer lumber. These are very good products. These laminated, they're very, very strong. As you can see, these LVLs are in a porch. I mean, they've got three LVLs here together. Spans really long distances, carries load really well, has very little deflection. Okay, You can also do rotated like 2x8s, 2x10s, 2x12s, and sometimes we do insulated headers, right? The energy code will require us to have an insulated header, so we just sandwich in a little bit of half-inch of insulating foam in between those three 2x, right? So that's perfect. Kind of works out almost exactly at 5.5 inches for us, which is the standard thickness of a 2x6, right? Okay. So when you're looking in your wall sections, you can see here's a typical header over a window, right? Anytime you got a door, header. Anytime you got a window, header, and you need to make room for it. So let's talk about pre-cut studs for a little bit. So what is a pre-cut stud? Well, it's a great question, because it's sort of a bad name in the sense that all studs are pre-cut, right? You can go to Lowe's, you can buy an 8-foot stud, you can buy 10-foot studs, you can buy 12-foot studs. Why is it that the contractors want to buy these ridiculous dimensions? Like, you'll even notice it that these guys are cheaper than, like, say, the 8-foot studs. So, and they work out to really, really bizarre dimensions, right? 92 and 5/8, 104 and 5/8. Like, why is that, right? It's a very good question. I'm going to switch over to AutoCAD and hopefully explain why we have these strange lengths and studs and why you would want to use them. So the contractor knows that for every wall I'm going to put my sill plate down. Doesn't matter if I'm starting my first floor or I'm starting my second floor, where I put my sill plate on top of my sheathing, which goes on top of my floor trusses, right? That I know he knows that I'm going to start with a single stud. You don't need more than that. And then you're going to put your pre-cut stud. Here's a 104 and 5/8, right? And then they know that the structural engineer is going to want me to have a double top plate. What's a double top plate? It's just two horizontal studs laid flat put together. You do the double top plate because you want to prevent, it's like a tiny little header, right? So the floor studs, or the floor trusses or the roof trusses, are going to be 16 inches, 20 inches, maybe 24 inches on center. But those floor and roof trusses aren't necessarily going to line up right on top of a wall stud. So to kind of prevent that, those little 16-foot 8-inch spans, those 16-inch or 8-inch spans or whatever they are from bagging, you do a double top plate. So when that's the that's the nice thing about it. So when I use the pre-cut studs, the 104 and 5/8, plus the 1.5 inches at the bottom, plus the 3 inches at the top, what I end up with, right, is a total distance of, snap it there, 9 foot 1 1/8. Okay, which is, again, it's still just another really weird dimension. Why 9 foot 1 1/8? Well, I promised the owner that I was going to have 9-foot ceilings. So how does this all work out? Well, I know that drywall for the ceiling has to be rated. So the drywall for the ceiling has a thickness of 5/8 inches. Okay, and I know that when I do my Underwriters Laboratories floor assemblies, I know that I have to have these 1/2-inch resilient channels, these little metal channels that run perpendicular to the truss, to the floor trusses installed as well. Which means once I lose that 1.25 inches total assembly, right? Once I lose that, 1.125 inches, then I end up with a beautiful number of 9 feet, which is fantastic when you're hanging drywall, right? So I get the ceiling hung, and then I have exactly 9 feet. How big is a piece of drywall? You can buy them in exactly 9 feet lengths. 8 feet, 9 feet, 10 feet. That's kind of 12 feet. I think you can even get 16 feet, but that makes it super easy on the contractor. They buy a silly pre-cut stud with a silly number, but once they put it all together, the drywall comes out to be perfect and they don't have to cut sheets of drywall. Everything goes in super fast. That's why they use pre-cut studs. It's designed to help a wood structure so you basically don't have to cut anything. You don't have to cut thousands of pieces of drywall. You just slap up every wall, no cutting. Saves days, weeks of labor costs, okay? That's why we do pre-cut studs. But it can make math a little bit more challenging, but there you go. Okay, let's talk, I have this diagram here. Let's go back. Just this is again a good example of the load path. This is why we use headers. Here's a good example of a window. I don't want the 3 stories, theoretically, or whatever it is up above this window to crush the window. So I have to transfer those loads into stud packs left and right of the window. Same for the doors, right? Easy peasy, just make sure you have room for them. Let's talk about sheathing. Okay, so sheathing is either a kind of a plywood or an OSB, usually 1/2 inch thick wood product that we apply to the exterior walls, to breezeway walls. Sheathing is used on the underside, on the top side of your roof trusses. Anywhere, basically, it allows you to have a flat board, continuous flat sheets, so you can nail stuff to it. Really, that's one of its primary reasons, right? Like it would be very hard to put fiber cement siding directly like on wall studs, and you can only nail it every 16 inches on center. Here I can do my nailing patterns every 8 inches on center, and I have something to nail into, right? The other nice thing about sheathing is it allows you to apply a weather barrier to it, right? You have to have, let's go back to this real quick. It's like this dashed line, right, behind your brick or behind your fiber cement or whatever, your vinyl siding, whatever it is you have in your building. You have to have something that stops the water. Okay, that's where this weather barrier comes in, and which is why we use this green sheathing, this zip system sheathing, is because the weather barrier is put on or applied, sprayed on to the sheathing in the factory. So they don't have to make a second loop around the building with Tyvek. Your weather barrier is built into the product, which is super nice, right? So when you're detailing it, you know, this is what it looks like in section, okay? So all they have to do is come back and tape the joints, and then your weather barrier is complete, which is why we use zip sheathing almost exclusively. Okay, we covered load paths. All right, let's talk about framing in general. Let's talk about floor trusses. Take a look at this photo. This photo tells you a lot. So you can see that double top plate we just talked about. You can see the header. You can see the little cripple studs I got in there just so they can frame out the window, but these little dudes aren't carrying any load. The load is carried horizontally up above. Here, this is your typical floor truss. Notice that it's made out of 2x4s. Almost all floor trusses are made out of 2x4s when it comes to wood construction. Notice that the truss is rotated so the 3.5 inch plate is facing downward. Okay, that's just how they do floor trusses. That is typical. I want to point that out to you because the roof trusses will be rotated 90 degrees from this, and it has to do with how the structural loads on these pieces are being applied. Okay, not gonna get into all the ins and outs of why. It's just I want you to be very cognizant of it when you're drawing it. That I see a lot of folks see, here's me, I've got these are my section for my floor trusses. That 3.5 is rotated long side down. And when you go up to the roof trusses, it's long side up. Just has to do with how these things are loaded. Again, not going to get into it, but there you are. Okay. Trusses are open so that you can run You can see all the things that go into them. Here's your main electrical feeds in gray, flying through the building, going to all the different electrical panels and all the units. Your orange in here, that orange pipe is your fire sprinkler pipe in here. You can see a fire sprinkler head going to be installed. Here's your rough end for your electrical in blue, the plastic blue, the aluminum, and then of course the aluminum foil. Those are all your duct work. That's all your HVAC piping. These little metal nailer plates hold, or what kind of hold your floor trusses together. You got your general assemblies there. You see a lot of these little nailers on all these floor trusses. Sometimes they have to do repairs, sometimes they have to join them, but they're usually, these floor trusses are usually about 20 inches thick, and then you can see the 3/4 inch OSB sheathing nailed on top of that to start the next floor, right? So here you can kind of see building under construction. They've got their zip sheathing, their exterior sheathing nailed in, but they haven't got it taped on the first 2 floors. Here you can see those floor trusses making up about kind of a 2-foot, they call it, independent, you can call this whatever you like. It's kind of concealed space because you won't, you know what I mean? You won't be able to get to it because there's floor on one side and drywall on the other. Interstitial space, whatever you want to call it. And then here they are framing up the 3rd floor of this building. When it comes to floors, this is part of our Underwriters Laboratories UL assembly. We always do this. It was a product called Gypcrete. You can think of it as kind of like a really lightweight concrete. It's puddled out at like kind of 3/4 of an inch. Sometimes here you can see this fella, there's this purple stuff. This is sound mat. That just helps prevent noise transfer from one floor to the other. But either way, whether you use the sound mat or not, we always do kind of a coat of this lightweight Gypcrete. It doesn't, let's explain what it does. So what does Gypcrete do? Well, Gypcrete, really almost more than anything else, is a great way it works as a floor leveler, okay? So, you know, wood is a naturally occurring product, and especially when you try to assemble these buildings for 3 stories, you know, like this guy's sitting out here in Louisiana, right? And it takes us a while to frame all this stuff, even into the best of times, before we get what's called roofed in, aka that the roof sheathing is down, the roof felt, synthetic roof felt is down, and then the shingles go on. All this stuff is just exposed to the elements. So the Gypcrete does a really awesome job of kind of helping us get a product that can kind of warp and bubble and sort of have mounds in it back to a smooth level surface. So when you walk in, your floor isn't, the flooring that you put on there isn't totally messed up. Also, it helps with fire, which is great. It helps with sound, which is great. So Gypcrete's a super nice product that we get to have, and you can see it here. I've got my floor sheathing there on top of my floor trusses, and then you get your 3/4 inch of Gypcrete. Bear in mind that when you start the next floor, okay, you get your wood sheathing, you take the sill plate. Again, this one's an upper floor, so it doesn't have to be treated. There's no sill gasket, it's just your standard 2x6, flat side down, nailed directly to the sheathing. The Gypcrete gets poured later. You can't, I mean, you could, but you can see when these guys are pouring the Gypcrete, they're pouring it after the drywall is in, right? That's usually when the Gypcrete gets poured, right? You don't really want to expose the Gypcrete to the elements. You don't want it to get rained on, when you're pouring it. It's going to crumble, it's going to crack. It's not a product that you want to have get wet. So bear in mind as you work your way up. Next floor, directly attached to the sheathing, another pre-cut stud. Here's an interesting detail. All of a sudden I've thrown in a 1x, right? 3/4 inch. Why did I throw in a 3/4 inch? Because I lose a 3/4 inch of Gypcrete, but I still want that sweet, sweet 9-foot clear ceiling I promised the owners. I need to make that 3/4 inch up somewhere. That's where I'm making it up at. Just easy 1x. As opposed to 2x6, I throw a 1x6 in there. Easy peasy, right? The contractor knows, the contractor sorts it out. I don't even necessarily have to call that out. They usually just take care of that for me. But it's nice if you can manage to call it out so you get that 9-foot ceiling you're telling everybody that you're going to install. Moving on up, we are looking at the roof. Okay. Let's go ahead and talk a little bit about roofing. Here is your typical roof structure. Again, I want to point out that all of a sudden you can see it. These 2x4s, these 2x4s are rotated now, so they got narrow side up or narrow side down, depending on how you want to think about it. All roof trusses are like that. Huge space in there in most attics. We're going to talk a little bit too. You see this sheathing, this vertical sheathing in here? That's our draft stopping. Okay. Here's a standard soffit. Typical stuff. Draft stopping. What is draft stopping? Draft stopping, you need to have draft stopping unless you're doing a fully sprinkled building. What's a fully sprinkled building? That means you take the sprinkler heads and you put them in all your concealed spaces, right? We don't typically do a fully sprinkled building. We do an NFPA 13R, which is a residential sprinkle system, and that means we don't sprinkle the interstitial spaces, but we still need to protect them to a certain degree. So how do we do that? Well, to slow the spread of smoke and fire, we take a truss, or a series of trusses, and we divide attics into 3,000 square feet or less, or every 2 units, whichever is smaller. And we take OSB, we take drywall, whatever it is, and we just put that up against one of our trusses in the attic. And we kind of seal, we divide up these attic spaces into these zones, and that just helps slow the spread of fire. Okay, we usually call out the attic draft stopping on the roof plans. It is, let's see if I can find it. So here's one. Here's just nice big dash line, calling out a section, draft stopping in attic, refer to detail. And let's see if I can find a detail for it. Here we go. Here's your typical draft stopping detail. I list out basically, I show that draft stopping rolling around. I show it continuous from the underside of roof deck down to the truss plate there. And I say note 1A, and I list out from the International Building Code all the materials that are allowed by code to be draft stopping. A lot of times the contractor calls me up and say, well, hey, what can I use for draft stopping? I'm like, anything on that list is totally cool. Okay. Moving back. So, kind of covered floor trusses, kind of covered vertical siding, covered sheathing. I haven't really covered drywall extensively, but I feel like you guys understand drywall fairly well. We've got attic trusses. I think the only thing, we got a little bit of resilient channel, a little bit of Underwriter Laboratories covered. We kind of need to talk a little bit about soffits or eaves. This is what's called an insulation dam, and all that insulation dam does is allow the soffit, which is designed to let air into your building. That insulation dam is there to prevent the insulation from covering up that opening, and then 2, just scooting back and then closing off this path, because air needs to go into the soffit, around the above the insulation, and then out through the top of your roof. That's how you keep your roofs cool. Good ventilation on an attic will help your shingles last years longer than an attic that is not vented. Okay, in the summer, the sun hits those shingles. That attic isn't conditioned. That attic starts to become very, 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 very hot. Good venting keeps the temperature down to a roaring boil. Without ventilation, your HVAC, your shingles cook, which reduces their lifespan, and your HVAC system in your building has to work a lot harder to compensate for that additional heat that isn't being vented or dealt with in any way. Okay. Um, Attic insulation, while we're here, sits most of the time. We don't do underside of roof deck. We don't do on top of roof deck. The cheapest way to do it is just sort of on the truss bearing right here. Okay, right above truss bearing. It sits kind of above these little metal resilient channels, and it looks like. See if I can find a photo of it, like this. Okay, there's our bad insulation, freshly pinked fluffy cotton candy that sort of sits in between the roof trusses sandwiched in there, and then the resilient channels help hold it in place as well. Sometimes we do blown in insulation. The blown in insulation is nice because the blown in insulation will cover, like you'll see, like when you're in, if I were to be able to get into the attic and show you another picture here, this bad insulation kind of has these vertical gaps where the trusses make a gap in that insulation. Blown in insulation kind of takes care of that, and then a little bit more besides. Problem with blown in insulation is you have to have the ceiling drywall installed before you can blow it in, otherwise it'll just fall down onto the floor. There's your insulation installed on your exterior walls. We also do insulation on the demising walls, aka the walls between units, and that's mostly purely there for sound, just to kind of keep the noise from one unit from propagating into the unit adjacent to you. That's what all these little swirlies are all about. That's kind of your graphical representation of insulation. Okay. So, kind of covered roof trusses, roof truss rotation. Here's a reasonable example of a soffit. You can kind of see that you have your wall terminating. The truss itself sits, usually the standard distance for us is 2 feet. All right, you get your 2-foot dimension where the roof truss sits proud of the exterior wall. That allows you to have that room, one, just so the building looks good. It's a good visual thing. If you can do 3 feet or even 4 feet on these buildings, it looks even better. But 2 feet's kind of the bare minimum so that you can do your vented soffit, that you can have enough room between the undersided deck and the top insulation to have air pass through that cavity and vent out to the other side of the roof. What does that look like? Well, here's a couple of okay details. We don't, again, pay no mind to this fancy black baffle system or the fact that the attic insulation's on the underside of roof deck. We put our insulation down here, right? And we have a vented soffit panel. Usually it's this fiber cement soffit panel. It's got a bunch of holes in it to allow air in. Air goes in, it goes up, it goes out through the ridge vent. Or we do slant back roof vents, which are a little bit cheaper than ridge vents, but we're trying to do ridge vents. Ridge vents are very simple. They leave an opening in the roof sheathing, and they leave an opening in the roof synthetic roof felt, which you put over the sheathing. They leave a gap in the shingles. They put this little plastic thing down that allows air to leave, but water to not get in. And then they put the peak shingles, or the ridge shingles over top of that, so it all looks pretty clean and pretty good. When it's all done, it kind of looks like that, and air is allowed to escape. In a nutshell, that's basically what we do there. So there you go. There's from the bottom all the way to the top. Those are sort of, in general, the general components of a wall assembly. You can digest a lot of these components in greater detail by taking a existing job and looking at these existing wall sections, digesting a lot of these keyed notes or coded notes, however you guys do them. A lot of them time in Revit now, but they're all basically the same. But yeah, there you go. These are the basic building blocks, these pieces, parts, gutters I'm not really going to get into today, kind of fiber cement. Look at the James Hardie website. if you're confused at all about how fiber cement works and how it's installed. But there you go. In general, that's your kind of basic 101 to wall sections. From here, we'll get into special. We can do more in a later talk. We'll talk about special details. How do we do a porch? What does a porch look like? How do we do overbuilt gables? How do we do the roof for the porch? How do we do pop-ups in the roof? I think that's going to be sort of more of a technical talk for another time, but this, I think, is enough for now. I got about 45 minutes, as much as anybody can take of these sort of things in any given time. So we're going to end it here. I appreciate everybody's time. Let me know if you got any questions. Thanks.